here. What kind of argument?
Well,
So the floor is yours.
well, thank you. This is very generous. I will consume an unhealthy amount of coffee from this, I promise you. So of course, it's my pleasure to be here today, sharing with you some of the recent work I've done, trying to understand how ideas from geometry and topology can help inform our understanding of soft material systems, in particular granular. I'd like to start with my acknowledgments up front. This work was done in direct collaboration with Andrea Liu, Sid Nagel, Tom Lubensky, and these pair of excellent grad students, Carl and Sam, together with a research scientist, Olaf Stenman. Of course, I'd like to kind of more broadly thank the UPenn Soft Matter Theory group. It's been an incredibly stimulating intellectual environment to work in. And of course, the funding for this work came from the American Philosophical Society and Maxwell. So I'm sure at this part in the seminar series, you've heard many versions of the soft matter intro. Let me say that my own interests are in the world of soft materials. So it turns out that soft matter systems display an amazing variety of material properties. So for instance, I don't know the last time you thought about phones. For me, it was this morning when I realized I'd forgotten my shaving cream in Philadelphia. But a NASA press release once described these things as 95% air, 5% water, and yet they behave as if they're kind of soft, springy, squishy solids. Somehow the collective interactions of these simple constituents give rise to a type of solidity. Glasses are another canonical example of soft matter systems where, if you look on the atomic scale, they look like disordered fluids, but they too behave like solids, in some cases exemplary solids. So for instance, glasses can hold a monotonically thin edge, so you see them used like in surgical scalpels. Soft materials are also the kind of delicious emulsions of fats in amorphous sugar matrices that make our life so delicious. And also the so-called Bingen plastics that we use to clean those emulsions off of our teeth, hopefully more than once per day. The thing I'll be particularly interested in sharing with you today is my work in granular materials. So granular materials are implicated in everything from avalanches and earthquakes to fascinating soft robotic systems. But you don't need to go to kind of exotic systems to appreciate how weird sand can behave, right? So I was informed that there are actual sand beaches right here in Burlington. For me, growing up in rural Maine, I didn't have the pleasure of walking on a wet beach until I was in my 20s. But maybe if you have walked on a waterlogged beach, you've noticed that in the wake of your footprints, there's this raised ring of dried out sand surrounding each footprint, right? And it turns out it's because wet sand has this interesting shear thickening property, sometimes called the dilating property, where the harder you try to shear it, the more it resists shear deformations. The extreme other end of this is when you have just enough water to lubricate some of the frictional contacts between grains of sand, and you get very shear thinning behavior. Materials that look pretty solid, but as soon as you try to stress them, they kind of transition to a more fluid-like state. In between these two extremes, you get what is maybe my favorite animation of all time, at least in the category of granular materials, something of a caveat. Here's a worker somewhere in northwestern England, walking on a quicksand-like substance. And if you didn't know better, you might think that he was actually walking on a membrane suspended over some fluid media, right? Because, I mean, look, you can see these beautiful ripples emanating from each of his footsteps. At the same time, if you kind of look carefully as he hops so delightfully around the circle, you'll notice that he's actually leaving footprints in his wake, right? So apparently, even though you get these fluid-like ripples, this thing really is a solid, capable of undergoing plastic deformation and maintaining the shape of imprints on its surface. It turns out that granular materials are often perched like this substance right on the precipice between fluidity and solidity, or between mechanical stability and instability. You've seen this maybe every time you've sprinkled grains of sand on a sand pile and watched it trigger mini avalanches as the system tries to regain mechanical equilibrium. Or if you've spent any time in the Midwest, as I have, maybe you've seen some of these delightful but, of course, very serious safety illustrations indicating how precarious the difference can be between standing on top of a pile of grains of corn versus being tragically sucked under. So in this talk, I'm going to be interested in exploring these kind of granular materials, and particularly interested in looking at their interfacial properties. So how do these systems behave at the interface where you might want to mechanically interrogate them? The schematic outline of my talk is as follows. I'm going to start by introducing a simplified model of granular materials that we'll use as a touchstone throughout the rest of this talk. I'll then say a few brief words, introducing you to some ideas from topology, and then move on to Maxwell counting, which at this point can just be a bit of jargon, but by the end of the talk we'll understand as a way of thinking about the interplay between degrees of freedom and constraints in different systems in a very generic context. We'll use these ideas to understand the mechanical properties of our model system, and then I'll finally close the loop and talk about how the topological ideas I introduced in the beginning really help us understand the interfacial properties of these granular media. So obviously there are a lot of moving parts in this talk. It's going to be something of a rolling tour through a lot of ideas, but I guess I promise, you know, just like in your favorite Dickens novel, all of your favorite characters will meet up at the end. So, granular materials. Real grains of sand, it turns out, look something like this. And while that's kind of, I think, aesthetically beautiful, as a theorist, I find it extraordinarily daunting, right? Because this is about as far from a spherical cow as you could get, right? So real granular material has bizarre shapes, it has frictional interactions, sometimes complex electrostatic interactions. And the idea of modeling and understanding these materials in all of their full detail is something of an intimidating task. What we want to do then is try to capture just some of the most essential features of granular matter. So the two things that I want to capture with my idealized model are, one, the idea that granular materials are athermal, so we'll be working at 0 temperature. And two, the idea that the fundamental interactions between grains of sand are short-ranged and repulsive. Right? So grains of sand repel each other, exert repulsive forces when they're in contact, and otherwise they basically don't interact with each other. Okay, so the simplest model of such a system you might be able to write down is, for instance, a collection of soft, repulsive disks or spheres in 2 or 3 dimensions. The detailed form of the potential kind of doesn't matter for what I'll tell you about today. You can ask me for its implications if you like offline. In the back of your head, you can just imagine you're throwing soft spheres in a box, and the energetic cost is proportional to the square of the overlap between those particles. If you're interested in equilibrium systems, as we will be, then you can go one step further, because of course about every equilibrium state there's some regime of linear response, so some regime where you can assume the thing is like sitting in an effective harmonic potential. So you can go ahead and replace your packing of spheres, your packing of disks, with a disordered spring network, where every bead corresponds to the position of one of the particles in that equilibrium configuration, and every spring corresponds to one of the contacts. And it turns out even this radically simplified model of what we wanted to start understanding displays a lot of the rich phenomenology of real granular materials. Right? And in particular, it has precisely the right type of transition between mechanical rigidity, where a system can maintain shear stresses, and a fluid-like or mechanically floppy state, when either the density of the disks gets too low, or the number of springs in your disordered spring network get too few. So we'll be coming back to this idealized model throughout the talk. Before we start exploring the properties of this model, let me just introduce some ideas from topology. Right, so topology, I would argue in the last, I don't know, X years, where X is some number, has been increasingly used to understand the properties of physical systems, right? And what is it? It's often somewhat qualitatively defined, as maybe why the coffee cup I was just so generously given is the same as the donut that I wish I'd eaten this morning. I like to think of it as why it's hard to wrap an orange with a sheet of paper. Right? Every map maker knows that if you want to take the surface of the globe and map it onto the plane, you can't do that without making some sacrifices. Either you have to tear the sheet everywhere, or compromise the areas or angles of the forms you're trying to represent. The version of topology I'll be particularly interested in is this notion of turning geometrical problems, like whether these loops are linked or not, into a counting problem. And the point is that, the mechanical behavior of these two systems is really very different. I can take the topologically trivial rings on the left and pull them apart as far as I want. But the fact that there's some topologically non-trivial character here imparts some rigidity to the system. It limits the extent of the definitions I can do. So let's explore this idea in a little bit more detail by introducing winding fluids. Right? So imagine you were going to draw closed curves, say on the surface of a sphere. You could imagine slowly changing that curve, slowly deforming it, until you shrunk it down to just a point. You would say you contracted it to a point. If you tried to play the same game on the surface of a torus, you would find, okay, sometimes you can do that no problem, but other times the closed curve you drew wraps around that central obstruction, it wraps around the hole, and so you can't keep shrinking it down. So it turns out then that every closed curve that you might want to draw can be uniquely characterized by a pair of integers, just how many times that curve winds around either the long or the short axis of the 2D. Okay, so that's great. You might well ask, what are the sorts of physical systems that have these topologically interesting surfaces? And what are the curves that are meant to do the winding on these surfaces that we want to topologically measure? To the first question, of course, I would just answer, well, there are many answers depending on what you want to study, but I would say Fourier space is the most natural representation. So recall, of course, that periodic systems like electrons in some periodic potential given by a crystalline lattice, Fourier space is the natural representation of things. So the natural basis for your wave functions is given in terms of functions that are periodic within the periodicity of the unit cell, and then some electron momentum terms. Okay? And Fourier space, of course, is precisely a torus, because as you take your wave vector k from minus pi over to pi, it turns out you've actually come back to where you started. So going from here to here is the same as going from here around to there. So I guess in a nod to all of my former English teachers, Fourier space is like a natural place around in which to wind. To answer the question of what sorts of curves are doing the winding, let me introduce the idea of geometric phases, or the Berry phase. I like to say it's, a theorem in quantum mechanics so recent that you can find a colored picture of the guy. So this object is called the Berry connection. And before I kind of unpack what it's doing, let me just say that a connection is just a mathematical term for how you transport vectors in space along curves. Right? And it's very easy to have kind of a natural intuition for this. Imagine you started at the east pole of the Earth, and you had a meter stick pointing due north. You then wanted to walk along the meridian, keeping that stick pointing in the same direction. You get to the North Pole, you walk back down along a different meridian, and then I guess very carefully walk backwards along the equator. And what you find is that even though you tried to keep that vector parallel at every moment, in fact, you've picked up some relative angle between your initial and starting configurations. This idea of picking up a relative phase depending on the curvature of the surface around which your curve is wrapping is precisely the kind of intuition that we're trying to capture So in the quantum mechanical case, the Berry connection kind of works as follows. You recall that the phase of the wave function is kind of ambiguous, right? Most observables don't depend on whatever absolute value of phase you assign. Of course, interference experiments depend on relative phases. And so you might say, okay, as I take some path in some space, if the phase of my wave function, for whatever reason, slowly changes as I go around that path, the Berry connection is designed to pick up changes in that phase. And so as you go around a closed loop, it's precisely the thing that can pick up relative phase contributions. It's going to be, I guess, about a 25-minute journey between now and when we see how these ideas apply to granular systems. But so let's just kind of keep this, I guess, in the back of our mind. Because first we have to talk about the mechanical behavior of these granular systems. So as a warm-up, let's just try to understand the distribution of forces in a sand pile in mechanical equilibrium, right? So if I tell you the grains of sand are all at rest, what forces do each grain exert on all the other grains? Let's start by just doing a simple problem in 2D, where I've just drawn in, 3 grains of sand, and I just want to understand what's going on with that third grain. Okay. So, gravity is pulling it down, there are 2 contact forces supporting it. I've drawn in some coordinate system for what the contact forces are. We've all done, I'm sure, many of these free body diagrams. As soon as you start writing down the equations of mechanical equilibrium, you notice a problem. There are 4 unknowns that we want to solve for here, each of the 2 components of each of the 2 contact forces. But there are only 3 constraints here, right? Force balance gives you 2 equations. Torque balance in the plane gives you just 1 constraint. And whatever boundary conditions you might want to impose, like static friction, no slip, whatever you like, don't combine to equal a new constraint. So we say the system is statically indeterminate. That is, just specifying that the system is in mechanical equilibrium is not sufficient to specify all of the forces. Just as systems can be statically indeterminate, you can also have dynamically indeterminate systems, where just specifying all of the constraints in the problem aren't enough to know if the system can move or not. So here's a classic linkage, a collection of rigid rods connected at pin joints. And you can see that there's this interest in rotary motion, which, happens to turn rotary motion into an effective linear power stroke and a recovery stroke. So these ideas were used by James Watt to invent the steam engine, or improve the steam engine. And the key point is that this motion doesn't involve changing the length of any of the bonds in that system. So it doesn't cost any energy to perform. So in general, when should we expect to find ourselves in statically indeterminate or dynamically indeterminate situations? An answer to this was given by Maxwell in the mid-1800s, and he gave a purely topological answer. Some might argue it was purely geometric. I'm happy to have that conversation if anyone's interested. And he said, let's just think about it in the following context. We'll just turn it into a counting problem and say a system is isostatic, that is, it has just enough contacts or just enough interparticle forces to exactly have a rigid structure without being statically indeterminate if the following 2 things are equal. Just the number of degrees of freedom in your problem, like the dimension of space times the number of particles, if that thing is equal to the number of constraints, like the number of interparticle forces. The nice thing about this being a purely topological answer is that it applies equally well to many systems, right? Granular materials, but equally well, for instance, understanding the distribution of stresses in, like classic engineering structures. Now, what Maxwell actually said isn't just the isostatic point is when these 2 things are equal. He actually said the number of zero-energy motions, the number of those like free mechanisms you should expect, is given by the difference between the number of degrees of freedom and the number of constraints in your problem. So the next few slides will just be a lightning round practice to get us all on the same page. Here I have 4 particles in 2 dimensions connected by 4 bonds. So that's 8 degrees of freedom, 4 constraints. Maxwell would say you should expect 4 zero modes. And indeed, there's a center of mass frame, so there are 2 trivial translations of the whole system, 1 trivial rotation. That's kind of trivial. But there's also this mechanism, a relative motion of the 4 particles that nevertheless leads to no stretching of any of these bonds, so it's cost 0 energy. Okay, a slightly more complicated example. Here I have 6 particles, 12 degrees of freedom, 8 constraints. Maxwell says 4 zero modes, and they're the same form. There's a center of mass frame for 3, and you get the same shear mechanism as we had in the previous slide. You can throw in an extra bond to get rid of that 0 energy mode, and 12 minus 9 equals 3. You can congratulate me on my hard-won subtraction skills later on. But what would have happened if we took this bond and put it over here instead, right? The count looks like it should be the same, but it's kind of obvious by inspection that there's a new 0 energy motion, the same one we've been seeing this whole time. So what's going on? The answer was provided, well, Maxwell knew about it, but the answer was rigorously provided by Caledine in the late 70s. And he said, you have to remember that you can be statically indeterminate. If you're statically indeterminate, you can have what are called these states of self-stress. So these are sets of bond tensions or compressions that lead to no net force on any of the particles. Here I've drawn in a simple example. So you can imagine if you take the 2 cross bonds and put them under tensions, they push out. Take the 4 external bonds, put them under compression. You could arrange the relative magnitudes of those so that there was 0 net force on each of the 4 corners, right? So that would be a state of self-stress. And Caledine said, in what you might want to call an index theorem, that it's this interesting difference between the number of 0 modes and number of states of self-stress in a given system that match on to the number of degrees of freedom minus the number of constraints. Now I want to point out that these are not just kind of interesting curiosities. These states of self-stress form a mathematical basis for thinking about the elastic response of your systems. So in particular, if you want to know the energetic cost of a given deformation, you can write that energetic cost in terms of a sum, in terms of projections over a sum of all of the states of self-stress in your system. So ideas like this are really used in practice to understand the elastic moduli of materials, or what their response might be. Here's just a fun bit of eye candy that I found of engineers understanding exactly how fault tolerant their airplane wings are. I really believe this promotional video was meant to be reassuring, and I did not find it so as I was flying over here last night. But anyway, you might ask, so far all of the systems that I showed were simple arrangements of particles that you could analyze by eye, right? So how do you imagine taking these Maxwell counting ideas to complex systems, like the sorts of large simulations of model granular material that I claim that I'm interested in, right? The answer is to turn to geometry, right? And so in particular, you want to introduce these 2 objects, the equilibrium matrix and the compatibility matrix. The equilibrium matrix is an object that says any vector of bond stresses, it returns a vector of the net force on each node. Similarly, the compatibility matrix takes a vector of node displacements and tells you how much each bond has to strain in order to accommodate that motion. Right. These, of course, rely only on geometrical information. So if I tell you what the pattern of connectivity between nodes are, and I tell you the node positions, that geometry is sufficient to completely and easily reconstruct what these matrices have to be. It turns out they're intimately related to each other. It's an exercise of, if you like, an application of the principle of virtual work, that these 2 ways of writing down an energetic cost, either displacements times forces or stresses times strains, have to be equal to each other. And so plugging in the definitions, you can learn that the compatibility matrix and the equilibrium matrix are just transposes of each other. With that in mind, you can write down an energetic cost for a pattern, say, of particle displacements by just, copying some stuff and remembering your factors of 2. And it turns out this operator, QQ transpose, is like a Hamiltonian for your system. Right? And that's great, because if you have an object that gives you the energetic cost of particle motions, of course, its null space gives you the zero energy motions. It gives you the null, it gives you mechanisms. It turns out analogous argument can convince you that this suspiciously similar looking operator, Q transpose Q, has a null space comprised of the states of self-stress. So this is great. We've turned kind of our problem into one of geometry and linear algebra. And of course, those are things that we know how to solve. So for instance, you can use these ideas to then start asking, okay, if you have a model granular system and you start interrogating the surface, you ask what its zero and low energy vibrational modes are, this kind of formalism allows you to easily understand the length scales and spatial organization of the mechanical response there. I'd like to take a brief aside to mention that, again, these states of self-stress can be usefully thought about to create what I want to say are kind of interesting new materials. So recall what Caledine said, the difference between zero modes and states of self-stress is given by the difference between degrees of freedom and bonds. So if you started with a spring network and you imagined removing a bond, probably you would remove a state of self-stress. Or if you added a bond, you would probably add in a new state of self-stress. So one of the things that I looked at was a way of kind of uniquely assigning a state of self-stress to any given bond in a disordered network. And you can imagine, since the states of self-stress are a basis in which to express the elasticity of these objects, you could imagine taking a spring network and adding bonds or selectively removing bonds until it had precisely the kind of designer elasticity that you might want. So I think understanding the spatial organization of these stresses would really allow for interesting new materials to be designed. Of course, it turns out that the spatial organization of these states of self-stress display some interesting scale invariance as a function of distance to the jamming transition, a critical point in this case. For the aficionados, one of the interesting results of this study was that the length scale, the diverging length scale associated with that scaling collapse, turns out to have a very unusual exponent, one that hasn't been seen to date in jamming literature. So it's kind of an interesting result. And maybe you're not quite as excited about grains of sand as I am. It's hard to imagine, but I guess I have to at least admit that's a possibility. I want to stress that these ideas of Maxwell counting are really quite generic. So for instance, you could stare at this assembly of rigid origami and start thinking to yourself, okay, the degrees of freedom here are like the positions and orientations of each of these faces. The hinges between the faces provide my constraints. And so I can think about what kind of mechanisms can I get out of origami. A canonical example is this so-called Miura fold, which is a simple origami pattern that can take a big flat sheet of paper and flat fold it into a nice compact package. In fact, this very fold was used to send solar sails into outer space because they could package the solar panels up in some tiny little cargo pod and then easily unfurl them once they got there. And I've used similar ideas about thinking about the mechanisms involved in these kind of origami structures to design kirigami patterns, so origami plus cuts, to make a single pattern that can assemble and disassemble into a wide variety of possible target structures. Right? So it's kind of okay, so now we have all of the pieces in place to understand where the topology enters our problem. Right? We have degrees of freedom and constraints. We have zero modes and states of self-stress. We're ready to go. So one thing that you might ask, of course, is can any of these simple mechanical systems that I've talked about, like origami or like collections of masses and springs, have topologically interesting properties? One of the very interesting advances in the last few years, due to Charlie Kane and Tom Lubetsky working at Penn, was to make this observation that the vibrations in some of these marginally rigid mechanical systems can be formally mapped onto the problem of the electronic states in, for instance, a superconducting polymer that we know has interesting topological character. So in the next few slides, let me unpack what that analogy really is. And we'll start just with our constraint count. Right, so here is a bunch of rotors, so each of these sticks can just rotate about that cross freely in the plane, and there are 5 springs that are coupling them together. So if I ignore the boring center of mass motions, there are 6 degrees of freedom here, there are 5 constraints. Maxwell would say there's one zero mode, and indeed, we find that there's a mode that sits on the edge. So the edgemost particle vibrates quite a bit, the next one less, the next one less. You get exponential localization of this vibration. Where might the topology be lurking in this description? Let me answer that by starting to build up a mathematical expression. Okay. So we'll start with K. So let's imagine not that we have 6 rotors, but that we have an infinite chain of rotors, so that I can really think about going to Fourier space and working in that language where I know that there's like a torus hidden somewhere. I'll then take the compatibility matrix, a function of the wave vector, and let me remind you that as a non-symmetric matrix, the compatibility matrix can have complex eigenvalues. Okay, just factors in your algebra. Of course, if it can have complex eigenvalues, then its determinant, which is the product of the eigenvalues, is just some number in the complex plane. So if you look at the imaginary part of the log of the determinant, you pick up what the phase of that complex number is. Okay? So this thing may not look particularly intuitive, but it's precisely the kind of geometric phase, Berry connection-like object that you can imagine doing loop integrals around Fourier space of, to ask if you can get any non-trivial windings. I want to make the connection to the electronic topological states a little bit more explicit. So let me remind you that I said you could write something like the energetic cost of a set of particle displacements with this Q transpose operator, and the energetic cost of something like applying stresses to all the bonds in terms of this Q transpose Q. So you could imagine writing down a combined Hamiltonian for all of these types of perturbations. Something like you gave it a vector of displacements and a vector of displacements followed by bond stresses, it would give you the total energetic cost. Right? If you did that, it would look something like this. It would be some block diagonal form. And what Kane and Lubetsky noticed was that you can kind of take the square root of this Hamiltonian, and you get something that has this kind of structure. Right? So first, let me just kind of wave my hands and be a guru and say that this kind of structure here is precisely what n equals 2 supersymmetric quantum mechanics looks like. And it's precisely matrices of this form that they made the connection with in the so-called Sushri-Verheeger model, right, where here the Hamiltonian is telling you something about electrons hopping from one sublattice of your polymer chain to the other sublattice. The point is just that you have some kind of interesting mathematical formal equivalence here, so that just as this object can be topologically non-trivial, so is there at least the possibility that these objects can be non-trivial. Right. And here it turns out that, what you would want to call a particle hole in the electronic version of the problem, it turns out that the states of self-stress and the zero modes are like the supersymmetric particles of each other. Okay. Now it turns out that the topological information embedded in these windings, which tell you about if you can have edge modes or not, don't depend on the fact that we played this Fourier trick and assumed we had an infinite lattice. So in fact, the topological information somehow even survives to considering finite lattices. One way you can pick this up is, for instance, by imagining gluing together two chunks of differently topological material. So if you take a few rotors here on the left that are in one topological state, and glue them next to a few rotors on the right that are in a different topological state, it turns out you can exponentially localize interfacial modes, either zero modes or states of self-stress, depending on what the two topological states are. This idea of kind of topologically protected interfacial modes between material of different topological class isn't restricted just to these rotors. It applies to bead spring networks of the sort that we're kind of interested in. So Kane-Lubensky also looked at this repeating three-site unit cell lattice and showed that if you take a chunk of material, which they were able to infer had some topological polarization, and wedge it in between chunks of material that were topologically trivial, you find that even though the counting says you don't need to have either zero modes or states of self-stress, the topological polarization kind of condenses charge, or condenses zero modes and states of self-stress onto those boundaries. So to date, a lot of the work in this field has been looking at simple lattices, right? So Kane-Lubensky looked at the one-dimensional chain of rotors, or a two-dimensional array of three-site unit cell lattices. I know my friend Zeb was here, I believe, just last week, and I'm sure he told you about his very exciting work looking at four-site unit cell lattices, where you can get really quite rich behavior in these topological systems. The question I have is, do these topological ideas have anything to say about disordered granular materials, right? One way of phrasing the question is kind of to look at Zeb's diagram here of kind of the configuration space of his lattices. So the idea here is that you fixed the location of three sites in your unit cell, and you imagine putting the fourth site anywhere in this unit cell. And then the symbols tell you, okay, if you put the fourth site over here, you'd be in a topologically trivial phase of matter. If you put it over here, you'd have some topological polarization. There are some shaded in regions where you get Weyl-type singularities. And so you might ask, okay, if you have configurations of the sort generated by throwing grains of sand in a box or compressing collections of soft spheres until they're mechanically rigid, do they live in a topologically trivial or non-trivial part of whatever the analog of this configuration space is? Now you might say, we already know exactly how to solve this problem. I told you that, just some winding number characterizes the topology of these systems. So just do this loop integral of the log of the determinant of your compatibility matrix and just tell me the answer. The problem is that for very large granular systems, this is a numerically completely unstable calculation. Okay? And so you have to be a little bit clever. So one thing you can do is to say, all right, well, the winding number here tells me something about the distribution and character of the protected surface modes in my system. So an alternate way to go about my problem is to directly try to study the surface modes and then infer whether there's a topologically non-trivial character to your states. Let me give you kind of just a flavor of this using a small unit cell, but we've done this for much larger systems. So I'll start with a collection, I think this is 16 sites, but I can't count that quickly. I'll start it next to a free surface over here, and then I'll play the rotor trick of imagining that it extends infinitely off into the bulk, like I have a semi-infinite chain of these unit cells. Okay. You could write down kind of an extended version of the compatibility matrix. So the diagonal terms here tell you if you displace particles within a unit cell, how do the bonds in that unit cell stretch? And the off-diagonal terms tell you about bonds stretching across unit cell boundaries. In this language, a zero-energy surface mode, well, it would have this form. This is just kind of definitionally to say nothing in a unit cell or across a unit cell stretches. And ansatz for solutions to these would be to have exponentially decaying surface modes, right? So the pattern of displacements in one unit cell would just be some, maybe multiplicative with some oscillating phase, but some multiplicative factor of whatever the pattern of displacements in the previous unit cell were. When you write it in this form, it turns out the whole game is what values of lambda, which is something like the effective decay length of these surface modes, allow you to find solutions to this equation. It turns out the set of allowed lambda are given by this determinant condition. So if the determinant of the diagonal plus lambda times the off-diagonal terms vanish, then that lambda corresponds to an exponentially localized surface mode. You know, I mentioned before that kind of the determinant problem was numerically unstable here, so you still have to be a little bit clever. And I'll speak to how you get around that problem in just one or two slides. But let's say that, you know, one version of did you find success with this project in finding topologically non-trivial states would be to play the same game that Kane Lumetzky did and say, if I can find topologically different lattice and I wedge it in between, you know, some other type of lattice, I should expect localized domain walls, right? So just as a teaser, of course, that's exactly what we find. So here, for just that smaller version of the system, you can see that again, even though the whole system is exactly isostatic, so there don't need to be any zero modes or states of self-stress, you find exponentially localized zero modes and patterns of stresses in your material. And I want to kind of give you the idea that you could imagine using these ideas to create, again, real interesting materials, right? So one thing you might think is, okay, if I have a state of self-stress that's localized at this point in the material, that means that as I apply an external deformation, that's where all the stresses are going to concentrate, which means that's where the material will fail first, right? So you can think about designing materials that fail in specific places in some topologically robust way. Like maybe you want topologically robust, I don't know, wrinkle zones or crumple zones in your car so that it doesn't fail near the passenger or near the engine block or something. Right? And people have really started playing with these ideas to create like actual materials that do exactly that. So here's kind of a lovely paper from Jason Pallosa and Vincenzo Patelli, where they topologically engineered states of self-stress to be in a particular point in their material, and then really showed that as they applied external stresses, that's exactly where the system buckled and failed first. Okay. I'll mention, kind of as a curiosity, to answer this question of what part of the configuration space do jam systems live in, it seems like from these small unit cell studies where we can do the full loop intervals quite stably, that jam systems generically live in a vile point-rich part of phase space, right? So these are, if you really had an infinite lattice made out of these things, these would be locations that kind of interestingly mixed surface zero modes and bulk zero modes together. From my perspective, this is a little bit of a curiosity in that for jammed materials, you're really kind of only caring about the Q equals 0 limit, right? You're not thinking about having a repeating lattice of buckets of sand. Okay. One of the things we were able to show, though, is not just the fact that you get these localized domain walls, but that the detailed statistics of the topologically protected edge modes we were able to find shed light on the jamming transition itself. So it turns out that there was a standard kind of theoretical argument in the community that was used to explain this figure. So this is the density of vibrational modes of a disordered jam pattern. And it has this funny boson peak, this interesting excess of extremely low frequency modes, where the frequency scale extends down lower and lower as you get closer and closer to transition. Interestingly enough, that standard argument relied on certain assumptions about what edge modes in these systems might look like. And since we were for the first time able to undertake kind of a detailed study of what they actually looked like, we could probe this theoretical understanding. It turns out that the assumptions of the theory were incorrect. In kind of graphical form, it assumed that these curves, as a function of system size wouldn't keep getting lower, but they do. So by doing this kind of topological study, we were able to show that, well, I guess more work remains to be done in our understanding of what we thought was a solved problem in the geometric community. All right, so we were able to show, just to reiterate, that at the point of marginal stability, these jam systems could exhibit topologically non-trivial states, which let you think about designing maybe new materials and also taught us something new about the jamming transition itself. In lieu of a summary slide, let me kind of give you the impression that this idea of exploring the interplay between geometry, topology, and soft matter systems is something that's really run through a lot of my research. So the same ideas about putting in defects and understanding the curvature of surfaces was precisely how I designed some of these origami patterns to assemble into a variety of interesting target structures. Our understanding of topological defects in crystalline systems has partly informed some of the machine learning work that I've done in an effort to find analogs of topological defects in amorphous materials. And the same kind of topology of linked and unlinked loops, it turns out, informs not just piles of sand, but also the dynamics of entangled polymeric fluids, either synthetic or biological macromolecules. So with that kind of teaser for some of the other work I've done, I'd like to just thank you for your attention and, of course, welcome any questions you might have.
Said about the boson peak.
Yeah. So it turns out in these disordered systems, right? Generically, for a crystalline system, you would expect there to be, some acoustic population of low frequency modes. So you'd expect the low frequency spectrum to go as omega squared for low frequency. An observed fact is that as you get closer and closer to the jamming transition, the actual density of states has a flat plateau that extends to arbitrarily low frequencies as you get closer and closer to the critical point. So a standard way of understanding why you got that particular boson peak involved kind of an interesting variational argument on what was presumed to be the structure of the surface modes. And it turns out some of the assumptions in that theoretical description, just trying to be tactful here, but turned out to be invalid. Turned out to be incorrect assumptions.
And so there is no explanation for the boson.
So that's right. So now we are at a point where there are a few kind of new competing ideas. So after we put this paper on the archive, the creator of that original variational argument, we had a nice email discussion, and a few days later he proposed a different explanation, the detailed assumptions of which remain to be checked. So at the moment I would say, yeah, the state of whether we understand this is unsettled.
What are the details of this computational instability you mentioned? What actually makes doing this a hard numerically?
Oh, right. Yeah, so somehow I think a slide either skipped over or deleted. It looks like it got deleted, which is fine. So the point is, yeah, so either this version of the problem, this version of the determinant problem has a slightly different difficulty than this version of the determinant problem. In this case, it's reasonably stable, but you have to compute this value at many values of wave vector, and then for every surface you want to pick. And so it turns out to be just too slow, because the numerical computation of any large determinant slows down pretty unacceptably. Right? So it goes as the eigenvalue problem.
That doesn't satisfy any stability, that's just a parallel.
Yeah. So that's a parallelization problem. This version of the problem really does suffer from instability in that you're looking for determinants of matrices, and they're achingly close to zero. So if you look at the characteristic polynomial of these things, if you do it naively, you get these ratios of polynomials in lambda that contain lots of terms that are, to within numerical precision, zero, but definitely can't be zero because, well, you know what order the polynomial has to be. So this version of the determinant problem suffers from numerical instabilities. This version of the determinant problem suffers from computational parallelization problems. That's exactly right. But in either case, solving the kind of sparse eigenvalue problem associated with this version is trivial.
Stay here. I have a question. Now, look at yourself.
Yes.
This radial stretching.
Mm.
Is that the artificially put in there?
That is probably because when I cut and pasted into PowerPoint, it must have distorted it. So these are supposed to be identical copies of each other. But staring at it, I can see what you mean, because the red lines cross the bonds at different points.
Right.
Good eye.
Oh, okay. So
Yes,
that's your
that
mistake.
is a mistake of the slide creator, not of the underlying mathematics.